James Bond. Shaken, not stirred. And then actually next week we're doing double E2 elimination. It's actually the name of the next James Bond movie. Don't know James Bond movies? Yeah. Double E2 elimination. Okay. Yes, shaken, not stirred this week. Okay. A substitution reaction. Okay. Any questions before we get started? Group lab report. Due when you come to lab this week? Pretty good yields on that. Seem to go reasonably well. Any questions about anything, guys?
Professor, you said it was 2 weeks, right, from Friday?
No, I never said that.
Everyone recalls that, right?
It's in the lab, but you said it was due next week.
We're only doing a 1 week lab. Instead of running the mass spec in lab, I gave you the mass spec
Understood.
handout. So it's just a 1 week lab.
Sorry,
Yeah. Okay, guys, we need to make some progress here on substitution. What type of nucleophiles can participate? Strong. How do we know which ones are strong? Okay. Anions are strong and sp3 amines. These are your strong ones. Anions. Are all anions strong? No. So we have to already be careful of exceptions. For example, Cl-, that's an anion. Is it a strong nucleophile? Not really. Okay? Your anions of strong acids, conjugate bases of strong acids tend to be pretty weak and lazy. Already we have an exception. Not all anions. All right? Also, if the anion is highly conjugated, it may not be that strong. But anions and sp3 amines are sort of the opening statement. And then quickly we have some exceptions. Okay, let's see here. Are these, which ones are strong? First one, strong? Is it an anion? Is it sp3 nitrogen? No, weak, not strong. Let's circle the strong one. Don't circle the first one. This carboxylic acid, strong nucleophile?
No.
I see lone pairs in several places. No, neither one of these are strong, even though they have a lone pair. They can act as a nucleophile. Anything with a lone pair can theoretically act as a nucleophile. Yeah, I think, yes. They're not strong. Those are weak. How about this one? Is it an anion? Yes. Yes, it's an anion because this is an organic chemistry and we know that's a spectator ion and this is really what? That's O-, anion, strong nucleophile. See, this is neutral oxygen. Neutral oxygen, not strong nucleophile. But O- anion is. Okay? Strong. How about this? Call it 1, 2, 3, propylamine. Strong or weak?
Strong.
Strong. It's sp3 nitrogen. Nitrogen's a pretty bad parent. Let's those kids get out there and do backside attack. Bam! Alright? Oxygen's a much better parent. Even though they're both neutral, there's a difference. Bad parent, good parent. Won't let the kids out of the house. Okay? What about this? Amine. Is that an sp3 nitrogen? Oh. What's hybridization of that nitrogen?
sp2. Oh, it's
sp2.
conjugated.
Long pairs in what type of orbital?
P orbital.
P orbital. We learned this during week 1, week 2 of the course. Okay? If the lone pair is conjugated, if the lone pair is in the p orbital, it's busy doing resonance and conjugating. Okay? It's not interested in doing any other reaction. Much less interested. Not strong. It's not an sp3 amine. Okay? Lone pair is conjugated. What is this? Actually, one of my favorite reagents.
Potassium cyanide.
Potassium
Cyanide.
cyanide. Okay? Or you can just say KCN. Right? I remember KCN, the Sunshine Band, back in the 1970s?
Not really.
Okay, certain. Good. Casey and the Sunshine Band. Casey and. Okay, what is this really?
K plus and C minus.
It's C and minus. We can show Lewis structure. Here we go. It's carbanion. The carbon is a carbanion. The carbanion here is the nucleophile. It's a strong nucleophile. It's an anion. Okay? Yes. Water. No, weak. It's not a nitrogen. It's not an anion. Water is just like an alcohol. Weak. Okay? There's 3 strong nucleophiles up there. The others are weak. Everybody good? I'm going to add one to it. What about F minus?
No.
Weak.
It's an anion.
It's a weak nucleophile.
But it has
F minus is actually a lousy nucleophile for a variety of reasons, which we're not going to go into. So not every anion, I tried to say, okay? Now, if you look at anions, there's the difference. What about I minus?
yes.
Is that a strong nucleophile? Well, that could be hard. Yes or no questions are more difficult. What about relative? Is this stronger than that?
Yes.
Yes, certainly stronger than that. F is a great parent, holds those lone pairs tight. Okay? But is this really considered strong? I wouldn't really expect you to know that. That's too much of an absolute question. Relative. I would expect you to know that it's stronger than that. Okay, so not all anions, so there is some gray area. Okay. At this point, let's put some of our knowledge to use, and let's do some precise examples of SN2. Some of these reactions will have names, very common reactions. First, let's deal with oxygen. Let's alkylate oxygen. Alkylation of carboxylic acids. Here we go. Can we alkylate it? Can we put an alkyl group on this oxygen? Okay, like this. Well, if we're doing SN2, and I've told you that's what we're doing, we need a strong nucleophile. Everybody agree? That's what we just said. Is this a strong nucleophile? No. Can we convert it to a strong nucleophile? Yes, by going to the anion. Can we convert this to the anion? Let's put some lone pairs here, okay? We're going to show charge, need to show lone pairs. That was in the, we said that first week. Incomplete structure there, yeah? Can we convert that to the anion? Yes. Let's put a bond here. What type of reagent would do this? Okay? Somebody tell me. You go to the stock room and ask for what? NaOH. Okay. NaOH would work. Okay. And what's the base? Hydroxide, right? These electrons take the H. These electrons move on to oxygen. You make that plus what?
Water.
Water. Okay, is this a good and strong enough base? pKa. pKa of the carboxylic acid? About 5. What's the pKa of the acid over here? Yes, water is 16. Which side's favored? 5 or 16? 16. By how much? 10 to the 11. Is this reaction favored? Yes. Yes, by 10 to 11. That's a huge number. Okay? Sodium hydroxide will deprotonate carboxylic acid and convert it to this. Now it's a strong nucleophile. Now we can come in with a carbon with a leaving group, an alkyl group with a leaving group, a tetrahedral carbon with a leaving group, and bam, kick off the leaving group. What does that give? Gives that bond right there. A lot of times I'll highlight a bond we just made. We made an O-carbon bond, yeah? Under my hand used to be bromine. Now it's the oxygen. Bromine, oxygen. Yeah? SN2. If we completely balance this out, in all this process we formed water. What else did we form, which maybe we can show over here? Sodium bromide? Yes. Everything's there. So we first have to make our nucleophile better. a strong nucleophile, then we can do an SN2. What did we do here? We converted the carboxylic acid to what type of functional group?
Ester.
Ester, right? We put an R group on the oxygen, converted it to an ester. Okay? It's a common way to make esters. Alkylation of carboxylic acids. We put an alkyl group on there by doing the SN2 reaction. Okay, what about alcohols and phenols? Glad we use sodium hydroxide up there because now we can consider it down here. Will it work down here? What about a regular alcohol? pKa of 16. Make this plus water, and it's also 16. Which side's favored? Which side's favored? Neither side is favored. It's a perfect equilibrium. At equilibrium, it's 1 to 1. That may sound like it might be okay, but it's not. In practice, it needs to be favored by like about 2 to 3 log units. Up top, it was favored by 11. This is no good. Not going to happen. No good. Okay? By the way, this is the same thing, right? There I showed the charge, and I'm adding long pairs. Here I'm just showing it like formula. You can do that, right? Right? Like if I show sodium iodide, aren't both of those things encircled the same thing? Okay? You got to recognize what you're working with. Right? Different ways to show it. And not think that, oh, this is so hugely different. No, it's just tomato, tomato. It's really more than that because nobody really says tomato. But half the people are going to show it one way, half the people are going to show it the other way. You got to be able to recognize both. Okay? This is O minus and sodium plus. Up there I didn't show the sodium plus. It's no good. We need a stronger base. Hydroxide, sort of the simplest base around, is not strong enough to deprotonate an alcohol. So how can we do it? We can use sodium. What's the charge of the sodium here? What's the charge of the sodium?
+1.
There is no charge.
Good, there is no charge. Because if there was a charge, I should have showed it. And if I might have shown it, then it's my problem. It's just sodium. What's the oxidation state or the charge? There is none. It's sodium 0. It's sodium what? Sodium metal. It's atomic sodium. Is sodium a metal? Yeah. I mean, everything over there is metals, right? It's just sodium metal. Okay? Why do I have to harp on this? Because I see students all the time, like, show a plus charge there, and then it's like, well, it's sodium plus. No, it's not sodium plus. If it was sodium plus, I would have showed a plus charge, and guess what? There would have been a minus with it. At least in practice, there has to be. Okay, you can use sodium metal here, and it's an interesting reaction. It's actually redox. And you will get this thing, by the way, what do you want to call this thing? What do we call this up here? This is the carboxylic acid. What do we call this? Nothing other than the anion. What's the name for them?
Carboxide.
Carboxide? No. Reasonable, but that's not the term used. Very reasonable. Carboxylate. Carboxylate anion. Carboxylic acid, carboxylate. Now down here, your ending's going to work. Alcohol. What do we call the O minus? It's not spelled with a C. Here, let's do like this. What do we call this? What if it was just O minus or O2 minus?
Oxide.
Oxide, you put an H on there, it becomes hydrogen oxide, and that can be shortened to hydroxide. This is an alkyl group on an oxygen. Alkoxide. Not hydroxide, but alkoxide. Anion. More fully, the sodium alkoxide. But you can also have potassium alkoxides. They're very common. Sodium is a touch more common because sodium is more easily handled. Potassium is much more reactive, a little bit more dangerous. If we have time, we may actually cut some sodium in lab. You saw sodium in Gen Chem? Did y'all cut sodium in Gen Chem? Demo it or anything? No? 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 Okay, sorry. Sodium will do this. It's not an acid-base reaction, though. We're not going to like show an arrow and take the H. We're not going to make NaH or anything. We actually make H2. It's actually a redox reaction. And redox reactions are harder to show mechanisms for, and they're most likely radical reactions, not showing a mechanism. Okay? Why is it called? What's redox about it? Well, the sodium here is sodium 0. What's the sodium over here? Plus. So the sodium went from 0 plus. So the sodium lost or gained an electron? In that scenario, it has lost an electron. But what is gained an electron? Well, over here, the redox here, this is considered H plus, or plus 1. Now, it's not charged, but that's how you consider this. What's the redox of hydrogen in the elemental form? 0. So you see, it has things that have gained electrons. The other thing about this here is it's not balanced. There's one H over there, there's 2 over there. Okay? If you want to balance it, please do. Okay? It's not balanced as shown. But guess what? You take an alcohol and you add in some sodium, it'll start bubbling. What are the bubbles?
Hydrogen gas.
Hydrogen gas. Okay? It's a redox reaction. But this will form the alkoxide completely. Imagine the first person who ever put sodium in alcohol and see the bubbles. That was the first. Then they went and told somebody. And then they figured out other things about this. Generate sodium alkoxide. You can actually generate hydrogen. Maybe you want to generate hydrogen to fill a balloon so you can then float it or something. It's a way to generate hydrogen. But in this scenario, we just sort of let that go because we're focusing on this. Another way to make your alkoxide is you can use sodium hydride. We've never seen that. What's the charge of the H in sodium hydride? Yes. H minus. We've seen that before when we talked about hydride shifts. Carbocation rearrangement, the H and the 2 electrons, and I said this is called hydride. Well, hydride actually can exist. Have you ever seen hydride before? Like sodium hydride? Anybody ever seen it? Okay. I got some in the lab. It can be made. It's rarely discussed at the intro level. But at this point, we're going to start discussing it. It's possible. And as you move into organic 2, you'll see other hydride reagents. But this can be a pretty strong base. And here it's an acid-base reaction, and if these 2 electrons bind to the H and these stay behind, what does that give? What are we making right here?
Hydrogen gas.
Yes, this also gives hydrogen gas, and it gives the O minus, and the sodium can sit with it, you make your alkoxide. Now this is a standard acid-base reaction, which we've been showing the standard mechanism for 2 or 3 months now. H minus as a base. But with sodium, that's redox. 2 different ways to make alkoxides from alcohols, which are less acidic. Okay? So here we go. We take an alcohol, treat it with sodium, we get the alkoxide plus hydrogen. Now we can come in with some type of carbon leaving group, like benzyl, chloride, and bam, kick you off. And we make that bond right there, that O-carbon bond. I agree we made the O-carbon bond. Oxygen is now bonded to the, this is a benzene ring. What do you call the carbon bonded to a benzene ring? Yes, benzylic carbon. Right? Okay? Oxygen is now bonded to the benzylic carbon. Alright? Used to be chlorine bonded there, now it's the oxygen. And of course the rest is there too. There's the bond we made. In the end, the alcohol was converted to what type of functional group? No longer an alcohol, it is now a ether. And this is called a Williamson ether synthesis. It's a very common way to make ethers. You make them from the alcohol. The alcohol has one group, one alkyl group on the oxygen. By doing an SN2, we put a second alkyl group on the oxygen. Alkylated the oxygen. We first had to convert the alcohol to a strong nucleophile. So strong nucleophiles are required for SN2, right? This is SN2. It's not SN1, is it? Yes, it's SN2. What about phenols? Well, phenols you can use hydroxide because phenols are more acidic. And so you make that plus 16. You do this. Which side's favorite, 10 or 16? 16 by 10 to the 6. Remember, all you need is like 10 to the 2 to be favored. 10 to the 6 is good. And so with phenols, we could react them with sodium hydroxide. We make the, what do you want to call this thing? Let's just call that minus, okay? What do you want to call this anion? It's not really an alkoxide because the benzene ring is not an alkyl group. Yeah. Yeah. It's called a phenoxide. Yeah. We can make the phenoxide using sodium hydroxide. Then we come in with a carbon leaving group, and bam. Well, wait a minute. I need to show a bond here. Bam. Kick it off. Basically, that's the simplest type of carbon you can have. That's just CH3. Type of tetrahedral carbon. Kick off the leaving group. That's methyl iodide. Very common for just supplying the methyl group for a substitution reaction. Replace that iodine and have other things bonded to the methyl. What's now bonded to the methyl? The phenol, the phenoxide, or however you want to say it. And the alcohol, or phenol, is now an ether. So it's another example of a Williamson ether synthesis. Williamson lived in the late 1800s and started making a lot of ethers this way. Mid-1800s. I don't know if Williamson was someone, I don't know if he was English, I can't remember. He was the one who grew up in maybe Buffalo, and one chemist grew up in Buffalo, and they had a chemistry lab in their out in the back of the house or something, back in the mid-1800s. I don't know if that was Williamson, maybe it was somebody else. Back then, they'd have like chemistry labs out around the house or something. Go out there and do chemistry. Yeah. But ethers, like diethyl ether. Now, Williamson would probably have had been more mid-1800s. Diethyl ether became very big during the Civil War as an anesthetic. How are you going to make diethyl ether? I mean, 500 years ago, diethyl ether did not exist in the world. But somebody came along and made it. And then it became like hugely important during the Civil War. And that's what chemistry is. I mean, making use of new compounds. Some compounds are natural, but a lot of times it's synthetic compounds, like drugs. I mean, a large majority of drugs never existed in the history of mankind 100 years ago. Brand new molecules. Okay, can we make rings this way? Yes. If you take this compound and treat it with sodium, you actually get this here. A cyclic ether. It is an ether, but it's part of a ring, a cyclic ether. And we can completely balance it out. What's happening here mechanistically? Sodium reacts with alcohols to give what? The alkoxide anion plus what? H2, so it's over there. What can that do? This can come back and bam! Attack the carbon, kick off the leaving group. And what does that give? It gives that, right? And then the Br minus, the leaving group is here, and the sodium cation that formed whenever you did the erythral redox is here, everything's here. If I see that, we can make rings by a substitution reaction. Everybody good? Y'all seem bewildered by that. No? What's strange about that? Okay, it should be pretty straightforward. And so intermolecular, we call that intramolecular, SN2. Okay, good. Synthesis. Can we go backwards? Williamson ether synthesis. I'm about to say that's maybe our first name reaction. When I say name, it's like a chemist's name. There's actually not. We had Dilzolder. We have Williamson ether synthesis. We had some names before. We have Markovnikov. That was predicting a sort of mechanistic outcome or route. Markovnikov was a Russian chemist. We'll have Hoffman coming up. Hoffman and Zaitsev. Zaitsev, I think, actually worked with Markovnikov. Some Russian chemists in the late 1800s. A lot of that chemistry came about because they were looking to make new ways to make vodka and improve industrial production of things. Can we go backwards? Williamson ether synthesis. Can you make this compound? Show a synthesis. How would you make that compound? First off, what type of functional group is it? Ether. Okay. What's a common way to make ethers? Williamson ether synthesis. Which involves what? Starting with what? Alcohol. And what do you do with the alcohol? You convert it to a better nucleophile by converting it to the alkoxide. And then you react it with what? Basically, all my answers we just went through. We just showed how to do a Williamson ether synthesis. Now do one, but do one to give this product. What we're going to find is there's actually two different Williamson ether syntheses we could show. We're going to have to decide which is best. Anybody got one? essentially, yes. I would just sort of show it or present it a little bit differently. The way you presented it, I'd probably show the alkoxide, then show your thing with the. I'll mention that when we sort of do it, and I'll show you. But yeah, you essentially you've got it. Anybody else? And you've also got the correct. Can you show the other? Show the other possibility. Anybody show both? Anybody else got something? Yes, but like on the quiz, you guys got to be careful. Going from something that has 8 carbons and then all of a sudden have 9. Somebody got that on the quiz?
Yeah.
Yeah? Okay. You got it? Okay. Now be careful with that. Anybody else got something?
Is that a double bond?
I'm seeing some different leaving groups. Do you have to use the same leaving group? No, you have a choice of leaving groups. We have a problem.
Oh, I see. Yeah.
We got it. Can you use any? Is choice of base important? We look at choice of base. Factors there. What are your base options? When do you need to use a stronger base? Anybody else? Okay, here we go. Basically, we're going to make an O carbon bond. Do we want to make this one or that one?
The right.
Did you realize there were 2 choices?
The right.
Let's go backwards. A retrosynthetic arrow. We can go back to, how about A? A would come from reacting maybe that with that. If these 2 reacted, would it give the A bond?
Yes.
Right, SN2?
Yes.
What about the B bond? That would be that plus I'll take the bromine. Bromine is the best leaving group. Well, be careful. Iodine is the best. Problem with iodine is those compounds tend to be more expensive, a little bit unstable. Talk about that later. Bromine is almost as good as a leaving group. Much cheaper, much more stable. Most people use bromine. Okay. Chlorine. So I wanted 2 examples. Chlorine not as good of a leaving group, right? What about F?
Not at all.
F is bad. Okay. No, not a good leaving group. So this would be, that's the A, this is the B. We're going backwards. This double-lined arrow retrosynthetic. We're thinking backwards here. Right? I went backwards to those 2 possible. Which route is better?
B.
Which looks better? A or B? The answer is B. Because here the leaving group is on a primary carbon, but up here the leaving group is on a secondary carbon. Which would be better for SN2? Primary. Sterics is bad. Okay? The best would be down here. Now, typically you want to start with neutral. What I would do is I would then come back, okay, after I did my retrosynthetic analysis, think about it going in reverse. Now let's just come forward. I would start with that alcohol. And I'm going to do this all under one arrow. I'm going to do 1, 2, 3, 4 in terms of step. What's the first step I'm going to do to this thing?
Turn into a.
I got to convert it to a stronger nucleophile using what? Not sodium hydroxide, this is an alcohol. Sodium or sodium hydride. After I do that, I can come back and do what? React it with that. Would this give the ether? Yes. Two different steps. And when we first looked at line reactions, I showed you this, that handout. Okay? All right. If you don't put the 1, 2, you're not good, because you cannot mix sodium with this, and I won't tell you why. But we're not. That's not there. We first react sodium with that. Then when that's done, the second step is to add in this alkyl bromide. And that's how I would present the reaction a little bit. Okay? Everybody good? You'd rather have your leaving group on primary carbon. And we had choice here which O carbon bond to make. You can try the one below on your own. For practice, I would actually show both and assess. And that's what you should be doing anyway, but I would actually show it out. Alkylation of sulfur. Can you do this with sulfur? Yes. Sulfur just below oxygen in the periodic table, very similar chemistry. This is called a thiophenol. You can deprotonate it with hydroxide. Okay? And instead of sodium, we could use lithium hydroxide. And that's going to convert it to the S minus. We throw in this guy and bam! Attack the tetrahedrocarbon, kick off the leaving group. And what's the product going to be? Is that right? On the right hand used to be bromine, and now it is what? Sulfur. S minus, good nucleophile, anion. Which is a better nucleophile, S minus or O minus? S minus, yes. They're both considered good, but S minus is better. Your body actually uses sulfur as a nucleophile a good bit. If you look up glutathione, glutathione is a tripeptide that is used as a sulfur nucleophile. Which amino acid has an SH group on the side chain? Dang, I was going to give 10 points extra credit on the next test. Whoever says it. All right.
Did you say it? Sulfonamide?
Cysteine.
Oh.
Huh?
I was
You knew it? Why does it make sense? Okay, well you have to remember. There are other ones that have sulfur. Methionine has a sulfur. Yeah? Right? But the sulfur, but it's not an SH group in methionine. It's an S methyl. Well, that amino acids that have a cysteine residue, that side chain can act as a nucleophile under certain conditions. Sulfur is a pretty good nucleophile. What about nitrogen? Alkylation of amines. Okay? Here, you take a carbon with a leaving group, ammonia. Good nucleophile, strong or weak? Strong. Okay. This can attack the tetrahedral carbon, kick off the leaving group. What does that give? Actually gives this. And the product is positively charged. Now you can include a base and remove the proton. Base takes H, leaves electron, and that's where the lone pair would come from. Okay? You can show a neutral product, and this is where bromine used to be bonded to the carbon, but now it's the ammonia, but with also an H. So it becomes this primary amine after the substitution reaction. Okay? And this would be a direct alkylation of the nitrogen. Problem with this is you tend to get polyalkylation. Because during the reaction, the H can be removed, not from Br minus. The Br minus will not take the H, because if it did, it would form these two, right? If it took the H. The pK of this is about -5, and this thing is about 10. Which side's favored, -5 or 10? You see, that is not favored. This is favored. This is how it exists. Okay? Br minus will not take the H. Again, you can add base to this and take the H, but Br minus will not. But actually, during the reaction, there's something else that can take the H. Another ammonia can. Because if ammonia takes the H, you would make ammonium bromide and make the neutral. That's 10, and this is about 10. So this is sort of 1-to-1. This can happen. But now, this becomes nucleophile again, and it can react again. And it's got to lose another H, but you can get a second alkyl group on. And that's a very common outcome. You're trying to just put one group on, and you end up with two. And some students will say, well, doesn't this exist as the ammonium bromide? How is this a nucleophile? I don't understand how it can alkylate again. Does it have a lone pair? No. Well, the answer is ammonia, plenty of ammonia here, can remove the H from this, and now it's a good nucleophile again. You can't tell ammonia not to do this. And once this is freed up, you can't tell it to not react again. It won't listen to you. And you're going to end up with two groups on it. If you only want one group, that's a problem. It's called polyalkylation. All right? Now you can look at one of the handouts in the back. You'll see examples. I'm not going to show that today. Maybe first thing next time. There's alternatives to direct. One is to use azide. Take the same starting material with sodium azide. What's the charge at the N3? Yes, minus, right? During week 1, I asked you to draw a low structure of azide in the workbook. Or maybe it was H azide. Low structure is, remember doing that? How many valence electrons at N3 minus? Remember all the questions to ask about? Okay? This is typical low structure of azide. But one of the terminal nitrogens can come in here and boom, kick that off. And now you have N3 bonded to the carbon. You can show the structure out. Now this, if you do hydrogenation, you'll cleave off 2 of the nitrogens and just be left with the primary amine. And so this is an indirect route to primary amine, where if you tried a direct route, you may likely end up with 2 or more groups on the nitrogen. This gives a good yield of the monoalkylated product, indirect route. There are a variety of other indirect routes which you will see in organic too. particularly starting with carbonyl compounds. Okay. Other than this being indirect, this also shows us sodium azide. Okay. We'll finish up here. Synthesis of quaternary amines, often called quats. You take this tertiary amine and heat it with this. I'm using this a good bit. Of course, it could be iodide, tosylate. We know a variety of leaving groups, right? This will react here and kick it off. SN2. What does that give? Gives this here. A nitrogen with 4 carbons bonded is called a what? Not primary, secondary, tertiary, but quaternary. Now, can that nitrogen lose an H to go neutral? No, it doesn't have an H to lose to go neutral. In the end, you can isolate just that right there. And I can say, hey, this is that compound. I got nitrogen ions and I got bromide ions. It's called a quat. It's an ionic product. Are they useful? Have you ever seen quaternary ammonium salts used in a biology class we talked about? Okay. They have antibacterial properties. This one right here, where it's got 2 methyls, dimethyl, but it's also got 2 decyl groups. Didecyl dimethyl ammonium chloride. You ever been to the Y over here on Wheeler Road? And they've got the gels on the wall where you do your hands. Okay? If you look at the tag, it says didecyl dimethyl ammonium chloride. And when I saw that, I went, well, I'm going to add that to my handout. Okay? It's antibacterial. But you'll also see quats in biochemistry. For example, you guys know acetylcholine, acetylcholine? You know the structure of acetylcholine? It's choline with an acetyl group added. Well, here's choline, but guess what? Choline has a what in the structure?
Quad.
It's got a quad. Okay? And world record, the world's most bitter compound. It's the salt, but the cation is a quat. Okay, guys, we're out of time. I gave you a handout for, that's our next elimination. Okay. Have a good day, guys.